Hello, class. Today we're going to work with capacitors in a circuit instead of resistors. However, in this section we'll keep it simpler. For capacitors in parallel, have the same voltage across each one, just like resistors. However, what is different from resistors is how we calculate the equivalent capacitance for capacitors in parallel. We use this equation that is box. CEQ equals C1 plus C2 plus C3, which is kind of the opposite of resistors, so don't get this mixed up. Now, for capacitors in series, they have the same charge. It's kind of the same as resistance in series having the same current. But for calculating the equivalent capacitance in series, we use this equation. And again, it's the opposite of resistors. Okay, so our first example, we want to determine the capacitance of a single capacitor that will have the same effect as a combination. Take C1 equals C2 equals C3, which equals C. The first step would be to combine C2 and C3, but remember to use this equation. Since both values are the same, C23 equals 2C. Our circuit is reduced, and now we can combine the two capacitors in series. So we have 1/2 C plus 1 over C equals 3 over 2C. Then we'll take the reciprocal to get 2/3 times C, which is equivalent capacitance of the circuit. Now, conceptually, I would like to discuss RC circuits. RC circuits means resistors and capacitors in a circuit. When the switch is closed, it takes some time for capacitor to charge up. The value of the resistor in series with the capacitor will vary the time it takes for the capacitor to fully charge. Once the capacitor is fully charged, the current will stop flowing because the potential difference across the capacitor will equal the EMF, thus producing no potential difference through the circuit. So once the current stops flowing, the capacitor is fully charged and ready to be discharged for use. The rate of the capacitor discharging, its voltage, also depends on the resistor connected in series. Why is this useful? Well, actually, RC circuits are everywhere in electronics. A good example is a camera flash. In a camera, a capacitor is charged and ready to use once you hit the button. And then once you hit the camera button, a surge of voltage is released from the capacitor to the light that produces the flash. Another example is a pacemaker. Below is a RC circuit designed for pacemakers. In this circuit design, the capacitor takes some time to charge and discharge, but it doesn't fully discharge to 0, but instead to some value V0 prime. If you were to graph the voltage of the capacitor charging and discharging, it would look like the graph to your right. This type of repetitive motion is known as the sawtooth function, and a voltage varies with time, kind of simulates the motion of a heartbeat. Alright, so let's say in a circuit the capacitor is originally uncharged. We want to describe the behavior of the light bulb from the instant the switch S is closed until a long time later. Well, once the switch is closed, the circuit loop is complete. Charge will start accumulating on the capacitor. At first, the potential difference is high, thus producing a high current and creating a bright light. But over time, the potential difference across the capacitor becomes closer to the value of V0, because more charge is accumulating on the capacitor, thus creating less current and dimming the light. Eventually, the light will no longer shine once the capacitor is fully charged and equaling to the potential difference V0. So even very small circuits from 10 to 100 milliamps can be very dangerous, disrupting our nervous system. Larger currents can also create burns. So household voltage can be lethal if you're wet and in good contact with the ground, so be careful. And it's not the voltage that kills you, but it's actually the current. A person receiving a shock has become part of a complete circuit. You physically do not want to complete the circuit, especially if the current is high. In this example, the wiring of the air conditioner broke, but since the person standing is grounded, he has completed the circuit, and now the circuit is flowing through him, as seen in Figure B. However, most heavy-duty appliances have a third prom, acting as an extra ground in case any wire breaks in the device. And if you're touching the device, as seen in Figure C, you won't get shocked because of that third prom.